right, let's do some volumes by slicing. But we're going to do it about the y-axis this time. Actually, we're going to do it about the y-axis and the x-axis in this next problem. It's the same game, and I'm not going to get into a bunch of pictures with this one and a lot of talking. We're going to just start seeing, how do we do this? So there's our definition of the desk and washer methods about the y-axis. I don't want to put a lot of time into this. We're going about the y-axis now, not the x-axis. So if, say, we just had some sort of function, but now this function is x is equal to some, I don't know, p of y, we're going to go this way, where our radius is actually going to be the height x. It's going to be the height x. So which means it all needs to be in terms of y. So if you're going about the y-axis, everything needs to be in terms of y. If you're going about the x-axis, everything needs to be in terms of x. It's the same game. Outer radius squared minus inner radius squared, multiply that crap by pi. Let's just get into a problem. So I like this one because we're going to do both. We're going to get to see an example of both of them. So let R, we're going to figure out which solid has greater volume. Let R be the region of the first quadrant. All right, so just the first quadrant, bounded by the graphs of x equals y cubed and x equals 4y. Notice it's x is equal to stuff in terms of y, and x is equal to more stuff in terms of y. Now, which is greater, the volume of the solid generated when R is revolved about the x-axis or the y-axis? So let's see how we would set this thing up. So now you get my crappy pictures. Okay, so we're only dealing with the first quadrant. So we have to be able to draw x equals y cubed. We have to know which one's going to be our outer, which one's going to be our inner. And we're going to be thinking about it this way. The outer, when we're going about the y-axis, is the thing that's to the right. And our inner is going to be what is to the left. So can you draw x equals y cubed? Do you know what that looks like? It looks like this. But we only want what's in the first quadrant. Now, if we don't know how to draw our parent functions, we're, what's that word? What's that word? There's this word I was thinking of. Oh yeah, that's called screwed. Yeah, there it is, there it is, there it is. So we need to know how to graph our functions. So this is x is equal to y cubed. It's actually y is equal to the cube root of x. That's how we knew how to draw it. And then we're going to do x is equal to 4y. X is equal to 4y. Y is equal to 1/4 x. Oh, so it's just some line. And then we have some intersection down here. So here is our region that we're going to take. Oops, we don't care about B. I'm talking about B. I'm talking about B. That's when we go about the x-axis. Oh, come on. What a silly person I am. So this is going to turn out to be, sorry, not to scale. We're going to revolve it this way. Huh? Oh, look at my beautiful drawings, huh? Oh, let's go. I think we have it. What's our area function? Our area function is going to be pi times our outer function minus our inner function all squared. What's our outer function? Now remember, outer is to the right. And it looks like what's in purple, our x is equal to 4y, is always to the right as far as what's enclosed in the area. So that's going to go first. That's the outer function. So 4y squared. 4y all squared. And then our inner function, the one to the left, is our y cubed. Sweet! We got an area function. So it's pi times 16y squared minus y to the 6th. And I know I keep writing area function. And you're like, but just do the formula. Nah, because if you just think about it as the area, it works for all of them until we get to the next section. So now when we do our volume, we're like, no big deal. I'm going to take the pi out to the front. And we're like, oh, okay, so we're going to go from 0 up to whatever this y value is. This, oops, they call it C and D. So I'll call it D. And then this value down here. But we know that's 0, right? So we have to, we're now going about the y-axis. This is with delta y's. This is with dy, which means you need to use the y value. So we need to figure out what's that y value, which means set them equal to each other and solve. So y cubed, set that thing equal to 4y, and let's solve that bad boy. So we move it over to one side, set it equal to 0, do a little bit of factoring. Oh, there's our answer. So we get the y is equal to 0, y is equal to 2, and y is equal to -2, but that's not in the first quadrant, so we don't care about that. So we found out that our height d is just 2. Now we can do our integral. And I'm going to skip some steps on this and kind of just jump to the end. So we have pi times 16 over 3 y cubed minus y to the 7th over 7, evaluated from 0 to 2. Yeah? Yeah, I think so. So clearly, it's 512 over 21. 512 pi over 21. Just thought I'd skip those steps because screw the whole like plugging in numbers at this point in time. We should be able to deal with fractions. So there was our volume. 512 pi over 21. And just for some context, because we're trying to see which one's bigger, we're going to say it's about 76.6. All right, neat. Well, now we want to do this about the x-axis. So we want to see which one's bigger. So we're going to go from, let's zoom in. We want to now know, all right, well, now we want to take this thing, we want to revolve it about our x-axis. Our x-axis, which means we want to change these. X is equal to 4y. We don't want this in terms of y. We want it in terms of x's. So divide it out and you get y is equal to x over 4. Now we're going to do the same thing for our other function, where that's going to become, it's no longer x equals y cubed. We're going to hit both sides with the cube root, and we're going to find out that y is equal to the cube root of x. Neat. Neat, neat, neat. Well, what's this value right here? What's our b? What's our b value? Get some of that nonsense out of there. What's our b value? Do you really want to set this thing equal like this? Do you really want to do that? Is that the plan? I guess we can. Shoot, let's do it. Do you really want to cube up your 4? I don't know about that. Wait a second. Don't we know that y is equal to 2? We know that point of intersection where y is equal to 2, so let's use some frickin' logic, y'all. You know? Like, let's use this one. 2 is equal to x over 4. Let's multiply by 4 on both sides and find out that x is equal to 8. Or our b value is equal to 8. I think that's much better. Instead of trying to set x over 4 equal to the cube root of x. You know, you're going to get your answer, but it's a lot more work, and I'm all about that laziness, y'all. Not necessarily laziness, but efficiency. So now that we have our two functions here, sorry, getting rid of the noise. I am not good with organization or making things look pretty. My bad. So our area function is going to be pi times our top function squared. Our top function now. Oh, that's the cube root of x, or that's the cube root of x. So the cube root of x squared minus our bottom function, x over 4 squared. Now we can start to solve for our integral. All right, so the volume will be from 0 to 8 of pi times, stay consistent. What am I doing? 2/3 minus x squared over 16 dx. And oh my goodness, those numbers are going to be pretty bad, aren't they? I think those numbers are going to get pretty gross. I'm like turning the page. That's that other volume we were checking out. So we're going to get pi times, we're going to add 1 to that exponent. We're going to get 5/3. We're going to divide by 3, so we're going to get x cubed over 48. We're going to evaluate from 0 to 8. 0 to 8. And, oh, there it is. It's 128 pi over 15. Ain't nobody want to do this. You need a calculator for this problem. So there's the volume. So we found in 2 different ways. Going about the x-axis, going about the y-axis. Are we going to have the same volume? What's 128 pi divided by 15? This is 26.8. This is clearly bigger. So getting the volume about the y-axis would give you a much larger volume than you would get about the x-axis. They're not the same. They are not the same. And notice I did not do this by drawing any volumes. I just drew the functions. Just drew them in so I could figure out what is the outer and the inner, the right and the left, the top and the bottom. So we can set it up into our formula. It's not needed to have to graph everything, especially if you already know what the functions look like. For this one, your teacher would have to draw a quick sketch because I wouldn't know what's on top and what's on bottom. But if you do enough of these problems, you start to get much better. You don't have to draw anything. You just run through and you do your gosh darn problem. Whew! We are done with volumes by slicing. Are you as happy as I am? Well, we got to get to the shell method next. I don't know. Let's see what's up. All right.